Hello friends, welcome to the video lessons on electronic measuring instruments. In today's class, we'll try to solve some simple example problems on bridge circuits, and then we'll look into the details of digital type of voltmeters. Before we go to the present topic, let us recollect what all we have seen in the last class. We have studied about sharing bridge. It is an AC bridge used for the measurement of unknown capacitance in terms of known resistance and capacitances. And then we have seen what is a what is the dissipation factor and what is the power factor for a capacitor. And then we have seen what are the different types of errors that may occur in bridge measurements and how they can be compensated. Now, let us try to solve some simple examples on bridge circuits. The first example is the impedance of the basic AC bridge are Z1 equal to 100 at an angle 80 degrees, Z2 equal to 250, Z3 equal to 400 at an angle 30 degrees, and we have to find out the value of Z4. So the given data is Z1 is 100 at an angle 80 degrees, Z2 is 250, Z3 is 400 at an angle 30, and Z4 is unknown quantity. Now we know that according to bridge balance condition, Z1, Z4 should be equal to Z2, Z3. That is, the impedances, the product of the impedances in the opposite arms should be equal. It can also be divided into two subconditions, that is, the product of the magnitudes of impedances in the opposite arms should be equal, and the sum of the phase angles of the impedances in the opposite arms should be equal. Now here, looking into the magnitude condition, the magnitude of Z4 is simply 250 into 400 by 100. That is 1000. And look into the phase angles. Z1 is at an angle of 80 degrees and Z4 is unknown. Let it be theta 4. Z2 is at an angle 0 because nothing is mentioned, and Z3 is 30 degrees. So here, if you can see, Z4 is 250 into 400 at an angle of 30 divided by 100 at an angle of 80. So looking into the phase angle condition, it is 30 degrees minus 80 degrees. So it is minus 50 degrees. Magnitude is 1000 ohms and phase angle is minus 50 degrees. That is the impedance Z4, 1000 at an angle of 50 degrees. The second example, let us check. The impedance of the basic AC bridge are given as Z1 equal to 200 at an angle of 60 degrees, Z2 equal to 400 at an angle of 60 degrees, Z3 equal to 300 at an angle of 0 and 0 degrees, and Z4 equal to 600 at an angle of 30 degrees. Now determine whether it is possible to balance a bridge under this condition or not. That is, four arms are placed in a bridge circuit. We have to check whether the bridge can be balanced or not. That is, whether the output of the bridge can be made zero or not. Because unless the bridge is balanced, we cannot use it for the measurement of either unknown impedance or unknown frequency. So here in this particular values of the impedance is given, you can see the phase angle of the opposite arms, the sum of the phase angles of the opposite arms comes out to be 60 plus 30 degrees on one side, theta 1 plus theta 4, and 0 plus 30 degrees on the other side, theta 2 plus theta 3. So theta 1 plus theta 4 is not equal to theta 2 plus theta 3. So we can conclude here that the bridge cannot be balanced and it cannot be used for the measurement of unknown parameters. Then, third example, a Maxwell bridge is used to measure inductive impedance. The bridge constants are R1 equal to 470 kilo ohms. The bridge consists of actually R1 equal to 470 ohms, kilo ohms, C1 equal to 0.01 microfarads, R2 is equal to 5.1 kilo ohms, R3 equal to 100 kilo ohms. We have to find out Lx and Rx of the inductive impedance. We know that at bridge balance, the condition for unknown or the expression for unknown resistance Rx is given as R2 R3 by R1 in a Maxwell bridge. So it is 5.1 into 10 power minus 3, that is R2, into R3, that is 100 into 10 power minus 3, divided by R1 is 470 into 10 power minus 3. 10 power minus 3 gets cancelled out both in numerator and denominator, and 5.1 into 100 by 470. Let us check what value it comes out to be. What is the values? 5.1 into 100 divided by 470. It comes out to be 1.085 ohms, or you can write it as 1.09. 10 power 3 is there, so 1.09 kilo ohms. And in Maxwell bridge, at bridge balance, the expression for unknown inductance Lx is given as R2 R3 C1. R2 is 5.1 into 10 power minus 3. R3 is 100 into 10 power minus 3 into C1 is 0.01 into 10 power minus 6. Sorry, these are positive values. Let me correct this. R2 is 5.1 into 10 power 3. R3 is 100 into 10 power 3. and C1 is 0.01 into 10 power minus 6. Now you can see 10 power 3 into 10 power 3 is 10 power 6 into 10 power minus 6. That comes out to be 1. So, and one more multiplication, 100 into zero point zero 0.01, it is 1. So, 5.1 into 1. So, its value is 5.1 henries. The unknown inductance value is 5.1 Henry, and the associated resistance value with the inductance is 1.09 kilo ohms. And another example is on sharing bridge. The sharing bridge has the constants R1 equal to 1 kilo ohm, C1 equal to zero point 0.5 microfarads, R2 equal to 3 kilo ohms, and C3 equal to zero point 0.5 microfarads at a frequency of 1 kilohertz. Determine the unknown resistance and unknown capacitance of the bridge circuit and dissipation factor. First, it is a sharing bridge. So we have to find out the unknown capacitance and the associated resistance for the capacitance. The expression for unknown resistance Rx is equal to R2C1 by C3. As you can see, R2 is 3 kilo ohms, that is 3 into 10 power 3. C1 is zero point 0.1 microfarads, that is zero point 0.5 microfarads, that is zero point 0.5 into 10 power minus 6, divided by C3 is zero point 0.5 microfarads, so zero point 0.5 into 10 power minus 6. So the unknown resistance Rx is equal to 3 kilo ohms. Then the expression for Cx is R2 R1 R2 by, sorry, C1 R2 by R1. So 0.5 into 10 power minus 6 into 1 into 10 power 3 divided by 3 into 10 power 3. 10 power 3 numerator and denominator gets cancelled out, and the left out term is only 10 power minus 6. Apart from that, zero point 0.5 divided by 3 comes out to be 0.166 multiplied with 10 power minus 6. That is the value of unknown capacitance. So its value is 0.166 microfarads. Then it is asked to find out the dissipation factor. Dissipation factor for a capacitance is given by the expression D is equal to omega R1 C1. Omega R1 C1. Here, omega can be written as 2 into pi into F. Where is pi? Where is omega? Here it is omega. Omega R1 C1. So it is 2 pi F into R1 C1. And that is equal to 2 into pi is 22 by 7 into F is 1 into kilohertz. So 10 power 3 into 2 pi F into R1 C1. R1 is 1 kilo ohm into C1 is 0.5 microfarads. That is equal to, now here 2 into 22 by 7 and 0.5. 0.5 into 1, 0.5, 0.5 into 1, 0.5, 0.5 into 2, 1. So 22 by 7 into 1. That is 22 by 7, 3.14. 3.14. And let us look into the exponential terms. 10 power 3 here, 10 power 3, 10 power 6 into 10 power minus 6. They get cancelled out. So the dissipation factor for the capacitance is 3.14. This is how we have to solve some simple example problems, even which may be asked in exams also. And here dissipation factor is a constant. It don't have any dimensions or any units. So these are few example problems. Then next we will go to the next topic, that is digital voltmeters, after a small break. Please